Is it visible now, SG?
Yes, yes, yes.
Good morning, everybody. Welcome back to the module 3. We are discussing about syntax analysis using context-free grammar. Actually, we'll see that it will actually be a subset of context-free grammar. So just to quickly recap, we looked at the basic structure of the context-free grammar, set of terminals, non-terminals, start symbol, and production rules, and some notational conventions which become handy to write grammar expressions quickly. And then taking some sample grammar, we have looked at the derivation process. Derivation process is the one where we start with the start symbol of the grammar, that non-terminal, and at every step, we use one of the production rules to replace the left-hand side non-terminal of that production rule by the right-hand side of the production rule. We keep on doing this till we end up with a string which comprise only of the terminal symbols. We call it the sentence. So that is one of the sentences in the language of the grammar. And all of the intermediate steps or strings that go through this process of derivation are known as sentential forms. And we have seen that there could be two very common ways of doing this derivation. One is called the leftmost derivation, where we always replace the leftmost non-terminal in a sentential form by one of its production rules till we complete the process. And other is the rightmost derivation, which is where we replace the rightmost non-terminal in the sentential form with one of its production rules till we end the process. And these are, so if a string can have a derivation, whether it is leftmost or it is rightmost, if it has a leftmost derivation, it will certainly have a rightmost derivation as well. And if a string does not belong to the language, it will neither have a leftmost derivation nor it will have a rightmost derivation. So the process of parsing is actually to form this whole stream of derivation, which can then be represented in terms of a parse tree. So we say that we will parse a given terminal string. That means that we'll start from the start symbol and keep doing the replacements and eventually get to the terminal string, get to the sentence. Or we could start from the sentence. That is, it is not necessary that the derivation will have to be constructed for a particular sentence in a forward manner, that is starting from the start symbol and doing replacements and finally getting to the sentence. We could also do the reverse, and that is what we will do for rightmost derivation. Is we'll start with the terminal string, that is the sentence, and keep on, instead of doing a production, we will start doing a reduction. That is, we'll identify a right-hand side in the sentential form and replace it by the corresponding left-hand side. And we will go in the reverse order from the sentence to the start symbol of the grammar. And if we are able to do that, starting from the sentence, if we are able to get this sequence of replacements or reductions, getting back to the start symbol, we say that we have got the rightmost derivation, and this sentence is a valid string in the language of the grammar. So what I mean here is the leftmost or the forward way of deriving is quite obvious, replacement by the production rule. The reverse way is like this, that if you consider this in the rightmost derivation, if you consider this ID plus ID star ID, this ID underscore is the last one that was produced in the forward direction. So what you say is, if we can somehow identify that this ID is actually the right-hand side of production rule 6, then I can reduce it, do a reverse replacement, reduce it by the left-hand side and replace this ID by F. And that F, now I can say that F is the right-hand side of this production rule 4. So I can reduce it, do the reverse replacement and get T out there. But that T is a right hand side of production rule 2, and I can replace I and get E. And then I can say that in the next ID underscore here, this is the right hand side of production rule 6. So I reduce it, I replace it by the left hand side F. Similarly, F back to T, ID back to F. Then I have T star F, which is the right hand side of T. I replace it, right hand side of production rule 3. I replace it back to get T and so on. So it is possible to go forward from the start symbol to the sentence, trying to kind of starting from the start symbol, some way to figure out what production rule to use for the leftmost non-terminal of the grammar, to so that we can eventually reach the sentence, the final terminal string that we intend to actually derive. Or we could do the reverse process of starting from the sentence, scanning it from left to right, finding out a string which is the right hand side of a production rule, and reduce by that, keep coming in the reverse order, and eventually reach the start symbol. So either of these processes is known as the parsing process. The first one, this is more example we did. The first one, which is the leftmost, goes top down because you start from the start symbol, which is the root of the parse tree, and keep coming down. It is a recursive descent process, as we'll see. But the other one, the rightmost derivation, we are following the reverse order. So it's bottom up, because at the bottom of the parse tree, you will have all these terminal symbols of ID, class, star, and all those. And you are starting from those and you are going up finally to reach the root, which is the start symbol. So both of these processes are possible. And a very interesting factor that works out is that there are several context-free grammar for which you can either have a leftmost derivation process, top-down parser, as well as you could have a bottom-up parser. But interestingly, there are grammars for which you may be able to construct a bottom-up parser, but you may not be able to construct a top-down parser. And there are context-free grammars for which you may not be able to construct a parser in this manner at all. And these are the kind of things that we are going to explore and check around. Okay, so we start. So this is kind of what we did till the last class. So what we start is we'll start with checking out what could be a possible way to construct a top-down parser. So there are a variety of top-down parsers. What we'll discuss here, and we'll be brief in terms of the top-down parser, because we won't do much of that in the actual C compiler. The one that we'll discuss is known as the recursive descent parser. So let's see what it says, what it does. It's something very, very intuitive. It's a very intuitive parser, very easy to construct, provided it can be constructed, and we'll see what the factors are. So let's take a grammar here. So here, without actually getting into, different explicit quadruple description of the grammar of terminals, non-terminals, start symbol, and production rule, we are just writing the production rule. So this is where we are using the conventions that we have set ourselves, that the lowercase letters are terminal symbols. Lowercase letters are beginning of the alphabet are terminal symbols. These single uppercase letters obviously are non-terminals. They're occurring on the left-hand side of the. So this clearly tells us that our terminal symbol set is A, B, C, D from here on the right-hand side. Our non-terminal set is S and A, because these are the only two which occur on the left-hand side. Production rules are given. How do you know the start symbol? Start symbol obviously is S, because you can see that if you start with A, then you will never use the first production. So that's kind of it's customary to write the productions from the start symbol at the beginning of the production rule list, but not mandatory. Okay, so it says that S produces CAD, and then A produces either AB or an A. So you can see that this is a very, very simple grammar, which actually can produce only two sentences, because as I start, there is no choice in the leftmost derivation to use anything other than this first production rule. So I get CAD. And then once I have got that, then I have to replace A. So I have two choices, either do AB or do A. So if I use A here, you can just put your attention at the bottom of the screen, bottom of the slide. If you do here, you get this derivation, which gives you CAD. And if you use the production A producing AB in the second stage, as in here, then you get CABD. Every other string comprising A, B, C, D are error. They cannot be derived from this sentence. So that's this is a simple grammar which has a language which is of finite size. So what you do here in the recursive descent parser is very simple. What you do is you need to do a leftmost derivation. Right? So the leftmost derivation means that you are trying to go left to right on the sentential form. Now you say that doing a leftmost derivation from or actually applying the production rule of a non-terminal is equivalent to as if calling a function corresponding to that non-terminal. And what would that function do? That function would, in its body, encode the right-hand side of the production. So what we do, few infrastructure stuff, that certainly your parser finally is the function main, and getChar, just doing a simple model, getChar gets you the next character. So you're reading the input. Now, as you read the input, you put it into a variable L, where you say L is a look ahead symbol. It is look ahead in the sense that L tells you what is the next symbol in the input. But it is said to be look ahead because it has not yet actually been generated by the grammar. So you take L as a look ahead, and we will continue to get L every time we do an operation. And eventually, when L becomes $, you remember our convention that input is always terminated by the $, to make it easy for us to understand that the input has ended. So when L becomes $, we have actually consumed the whole. When the look ahead becomes $, we have consumed the whole input. I think someone needs to be muted. Hello, please. Thank you very much. Okay. Now, so that is what he is saying. So we say that you read the first input character getChar, and then you have a function corresponding to the start symbol S. So that function, you call that function. So what you expect is that function will actually keep on going through the leftmost derivation process and keep on matching your input as it goes through that process. So that's the simple logic. And when this function returns, that is when you are done with consuming the input, hopefully, then you are back to main function, and at that time, obviously, you expect that $ should be in the input, in the look ahead. So if $ is the look ahead, then you have passed everything successfully. If not, then you have an error. So that's a simple. Okay. Now, how does the function look like? S is a function corresponding to the start non-terminal S. So what is S? S is CAD. So what do you expect? If this has been in the leftmost derivation, as S is replaced by CAD, certainly you know that the symbol in the input, which is L, must be SC. If it is not SC, you have an error immediately. Right? So to check whether it is this intended symbol C, you write an auxiliary function, a matching function called the match function. What does a match function do? Match function takes a character that you intend to match with and matches it with L, the look ahead character. If it does match, if they're equal, if it does match, then you know you are correct. So you are moving your input marker one step. That is, you have consumed the input symbol that was there as a look ahead. And as you do that, you just read the match function code. As you do that, this matching, then you read the next character in the process from the input. So you get to the next look ahead. If it does not match, then there is a disconnect between what your production rule expects to see here and what you actually have. So you print an error and the process ends at that. So that's the match function. So in terms of the match function, how you expect to express the production rule S, that is, if S has to do the derivation, then it has to first match C, because I have C on the right hand side. Then it has a non-terminal A, so it has to match everything that the non-terminal A can produce through the leftmost derivation. That is what we have assumed is represented by the call of the function corresponding to A. So you match C, then call A, and then after A has matched everything and you come back, the next look ahead symbol in the input must be a D. So you match D. And if this happens, then you are done. Right? So this is what. Now what is A? A is two production rules. Now you can see that so it could be the first production, it could be the second production. But in either of that, we see that the first symbol is A. So what we do is we blindly try to match A, because we know that if things have to be derived from A, as you can see here below, the check with line, A has to produce A or A has to produce AB. So when A produces something, the character in this case has to be A, small a. So you match with a small a. The similar matches happen. And the next character is read. Now there are two possibilities. If you're talking of this production rule, A produces AB, then L has to match B. But if A produces, if it is A produces A, the second one, then you are already done because you have consumed that A. So you check if your look ahead is B. If your look ahead is B, you do a match. The reason you still call a match, because match has two roles. One is to actually match, and the other is to update the look ahead character. So you do L equal to B and then do a match B to take care of the. If it is not a B, then what you expect? You expect it to be dollar, but it could be something else also, because your string could be a wrong one. So if it is not a B, then at least up to the expansion of A. I'm sorry. If it is not a B, then actually you do not know what it could be, because it is outside of this production rule. So we'll come back to S and see that it will have to be a D. So you still do not know what it is. But if it is not a B, then you know that this production rule is done with, and you are talking about the other production rule which has matched its A, and therefore you have to go back. Otherwise, if it is L, then you match with B and get the updated look ahead and then go back to wherever you came from. So you are back in S at this point. Your A has been expanded, whether it is in this case, the first case, or it is in the second case below. And then what you expect, according to the first production rule, CA has happened, then there has to be a D in the terminal string. So your look ahead L must be D. So you do a match D. It goes through this, adjust the look ahead to the next. You are done with S if it matches, and you are back here. Now at this point, certainly for success, you need the look ahead to be $1. If it is, then you are done. If it is not, you have printed it. So if you say this, then you can clearly see that if you finally reach the parsing successful, then you know that this string is derived from this grammar, and you have. And how do you actually get the leftmost derivation? That is very easy. You just need to put some more code to trace how the functions are getting called. So main is calling S, which is obvious. Now S calls A, so that basically you know then this A is getting expanded. Then A is calling this. So you just need to keep on tracing what functions are getting called, and you will. That's a programming task, and you will get what is the derivation that's happening. So it is quite obvious as to how the correct string will go. Let's look at one wrong string, say CAAD $. If we give this as input, what will happen? Where will it fail? So it starts at L, get cat here. L is C, comes to S being called, match C, that matches, goes to A, comes here. Then L at this point, after match C, L at this point must be the first A after C. So it match A, it will match that. So after it has matched, L becomes the second A. So it does not match here. So I go back from A to S. Here I'm done with I have actually done this production. A produces A, this production. My L now is the second A, but I need a match with D. I need a match with D. But my L is A. So this match D, when I come here, this will not match, so I'll get an error. So in this match, I will detect that actually this string is not derivable from this graph. So I have a parse error. So that's I have specifically taken an example where the language is finite. Language actually is the smallest possible, because if you have only one sentence, that's the smallest. But if it's one sentence, then there's no fun. But it's the smallest possible. It just has two sentences. But goes on to show you how you easily write a recursive descent parser. So at this point, let me pause and go back and check if there are questions, or if you are following really well. Okay, I'm back.
There was a question by Ishan earlier.
Let me see. Ishan, isn't the reduction method top down? No, Ishan, it's not. It's actually bottom. It's actually bottom up. Do not worry about the reduction method, because we will come to that, and we will go through a very detailed workout of how the reduction method works. I was just trying to. It's not top down because you're starting from the terminal string. See, the top down and bottom up, these two notions are related to the parse tree. So after the derivation, through the derivation process, we are constructing the parse tree. I'll show those as well. And the parse tree is rooted with the start symbol, and the leaf nodes of the parse tree are all has to be terminal symbols. Internal nodes are all non-terminal symbols. So the other interpretation of being able to parse a string is whether you are being able to construct the parse tree. So if you start from the start symbol and keep on constructing it downwards, then certainly you have a top-down approach. Otherwise, if you think that you have the parse tree initially as a forest of nodes, which are all individual terminal symbols in the sentence of the grammar, and then you are trying to club them together to go up, because they have to be some right-hand side of some production rule. So you go up, and you find the appropriate non-terminal on the left-hand side of the production to create intermediate nodes, and you keep on doing that till you get to the start non-terminal symbol at the root. Then you are certainly doing a bottom-up approach. That's the basic reasoning for the nomenclature. Okay, but we will take more detail, lot of detailed examples. Don't worry about this right now. Any other question?
Yeah.
So maybe I'm doing it in a too elementary way. Okay, good. Okay, so we are back to the recursive descent part. So let me just tweak this language around just a little, the grammar around just a little, and try to construct another recursive descent parser. So I'm going to the next slide. So all that I did, if you look at carefully, the first production I have not changed. In the second production, between the two terminal A, B, I have put in the non-terminal A. Third production I have not touched again. So just one change. But what does that change signify? That change signifies a recursion. That is, a non-terminal A can be produced from the non-terminal A, which means that I can keep on producing A like this for as long as I want. Okay? So this small change immediately makes it an infinite language. Okay? So that's what we are trying to do. You can see examples here, like whatever was CAD will still be accepted. CAA, CABD, which we had, you have to see whether that gets accepted. If that's not. So now this one, that's just the CABD. If you CABD was acceptable in the earlier grammar. Now you can look that CABD is not acceptable, because if you have done a production of CA with S, and A is expanded just by the second production rule, then you get the first string. For the other one, you need to do the other, so you get ABD. But moment you do this A, you need at least another A. So CABD is not possible. But you can now have as many A's generated as you want, because you can keep on recurring here. So for example, you can have CAABD, because you do this, S produces CAD, then you use A, the first production rule. So A produces AAB, so you get CAD gets CAABD, and then you use the second production to A. And you keep on, you can keep on, producing this to get parenthesized strings of AB coming around the final A. I mean, because every time you use this, you'll get a pair of AB. So that's a basic, basic language. I mean, that's just for familiarization. Now, what happens in terms of main? Nothing changes. In terms of S function, nothing changes, because there's no change in the production rule. But what will change in terms of A? Certainly, the first step does not change, because you still have, for both these productions, you still have a starting, which is a terminal A. So you do a match with A. And then for the look ahead, you have to see if what is the look ahead that you expect. Earlier, what did we do? Let's go back. Earlier, what we checked whether it is B or not, because that is a B that we are expecting. But now, certainly, if we have the second production, then your look ahead will be should be a D, if it is correct. Right? So I will go out. But if it is not, if it is this, then it cannot be B, because you have got an A, so you'll get something which is produced from A again, which means you'll get another small A at least one more small A, right? Because if you are using the first production. So after A matches, you check whether it is another small A in the look ahead. If it is a small A in the look ahead, then you are using production rule, the first production from A. If it is not an A, then you are using the second production. So you do this, you check for that. If it is, then what you have to match? You have already got the A. So you have to now check that what you get from this second capital A. So you call this function recursively here. So you can see that there's a recursive call coming in here, which actually produces that infinite set of strings. So every time you consume one A and then call A, or consume one A and then call it, consume one A and then call it. Now, when that series is over, as in here in one step, then you come out, and what you expect is after that there'll have to be a B. So there is a depth of calls that will happen, consuming as many A's as many times you have called A. And as the depth keeps on unfolding, unwinding, coming back, every time you come back, you expect a B to be matched. The look at, so you'll get that. So that ensures that you get this, matching pair of AB coming in here. And when you are done with that, you are done with this production. Rest of it is the same. There's nothing, no difference in this. Just the difference is in these three lines between what you did last time here. This is the last time's grammar. And this is the grammar that you have. And you can very easily see that how you could actually keep on generating longer and longer strings, and the parser would be able to detect that. So that's it's kind of it's some kind of a little observation. I mean, I would not say everything is just direct coding of the production rule. Obviously for S it is, but for A here you really need to do some analysis to decide that, okay, for the two production rules I can do that decisions together, and then the choice between whether I'm doing this production from A or the other production from A. Actually, I'm making some more, observations as to what can the strings derived from A start with. You're saying this is A. What does that mean? That means that you have analyzed to see that anything that I derive from A must start with the terminal symbol. This is the critical observation that you are making here, so that you can make this comparison. If this symbol were different, then you would have required to write it in a different way. So make that observation. I mean, we will see later on that there is a strong part of theory based on this, where he says there's a concept of first of a non-terminal. The first of a non-terminal is defined as the terminal symbols that can occur as the first symbol for any sentence that is derived from that non-terminal. The first of a non-terminal is the set of those symbols, terminal symbols, that can occur as the beginning of any sentence that you derive from that non-terminal. So you can say the first of S here is C. I mean, no matter what happens later on, anything that you derive from S must start with a C. Tells you that the first thing you need to do is match C. Otherwise the whole world is wrong. Similarly here, when you do first of A, you see that first of A is small a. So any string that you derive from the non-terminal A has to start with a small a, so you do a match A. There's nothing else that can happen. So that is the information, again, what you are using here, that after having matched A, if I have to call this the function for non-terminal A, then what do I expect in the input? It tells you the first of A is A, small a. So you expect a small a, otherwise it's cannot be. So there is some insight into this that needs to be involved. And the definition or very notion of first of a non-terminal gives you a very good clue in terms of how you can do this. But we'll come to those discussions later. But this is just a simple example of showing how the recursive descent parser can be constructed. Okay. So let us move on with more example. I present another grammar. E produces A E primed, and E prime produces plus A E primed or epsilon. Just spend a minute understanding the graph. What could be the simplest sentence that we generate? Now, quite obviously, E is the start symbol. Terminals are quite obvious. They are A or plus, just two symbols. Three production rules. Now, what could be the simplest string sentence? Is E produces A E primed and E prime produces epsilon. So it's A. The first example here. Look down below. Otherwise, what can happen? This is here is from E prime, the other production, the first production from E prime is a recursive one. So what does it do? Every time you call it, it will append a plus A to the earlier string. Okay? So if we do it the next step, E produces A E primed. Look at the second example. E produces A E primed. Then E primed uses the first production here. So it produces plus A E primed. So E primed is replaced by plus A E primed here. And then you use the second production of E prime to remove the E primed and have epsilon. You have A plus A. But this recurrence of the first production from E prime can be used as many times as you want. So if you use it, here you have used it once. In this first example, you haven't used it. Second one, you have used it once. The third one is you have used it twice. AE primed plus AE primed. Again, E primed you replace by plus AE prime. I've used it twice. Then you make it epsilon. You get. So if you keep on doing this, you can very easily see this is again the grammar for an infinite language where you are doing A plus A plus A plus A plus A plus. So it's like addition expressions of identifiers going as long as you want. So there is a nice observation to be made here. A very tricky one though is the fact that in whole of this you have a recursion, and that recursion is on the right. That is, you are always adding the plus on the right. You are not adding the plus on the left. Okay, okay, let's see how you code this. Just for practice, is quite main is quite the same. The getChar, the first look ahead, then call the function for the start non-terminal, final checker here, and you are done. What is for the first non-terminal E? Certainly will match A, which is the same function, match function, and then we'll call the function for E prime. What is the function for E prime? Okay, for function for E prime, now what we have learned? We have learned that to code the function for E prime, I need to know what to expect in the input. And what to expect in the input is from the first of the non-terminal. Now, what could be the first? What can be the first of the non-terminal E prime? Obviously, it could be plus, or it could be epsilon, that I don't produce anything. So I cannot obviously detect not producing anything in the input. So what I'll have to detect is whether I get a plus. If I got a plus, I'm going fine. If not, then I don't expect to consume anything and just say that this rule of E prime producing epsilon is vacuously true because it's not expected to produce anything. So let's see how we do that. So E prime produces a plus this. So I check if L is a plus. If L is a plus, then I do a match. Again, the same trick. I'm just figuring out that if I'm on the right track. If I'm on the right track, then I do a match. And if L is not a plus, then I know that there is nothing in the input that I must consume. So in the other case, I do not consume anything but just return. That's the case of the second production, the epsilon production. Otherwise, I've got a plus, so I match plus. Then I have to match A, so I match A, and then it recur on E prime. Keep on happening. So I keep on appending plus A, plus A, plus A as many times, and I'm consuming plus and A every time. I call this E prime. And then all of that stacks get unwinded. This time there's nothing to do when you are unwinding on the return. You just keep on return, done. Back to E, back to main, and at that time you must be at the end of it at dollar. Okay. So that's the simple way of writing a recursive design parser. I mean, this is the difference from the previous one. Two examples are previous two examples kind of looks abstract in terms of the interpretation of the language that they produce, but here we have a very concrete language because we have a language of addition operations in identifier. So if A stands for an identifier, then this grammar produces arithmetic expressions which are involving identifiers and addition of it, binary addition of it. Right? So we can actually have more generalization of this. Okay. Now, so if it does produce that, then our question would be that, well, whatever this language grammar produces, I can have a much simpler grammar which does the same thing, because all that I'm saying is an expression is either A, an identifier A, or it is an addition of two expressions. So if I say that, then the grammar could simply be E produces E plus E, and I have A separate. So that will produce an A like it did before. It will produce A plus A because E produces E plus E. This E could be A. The second E could also be A, so it gives A plus A. It could produce A plus A plus A. How? Because E produces E plus E. Then say first E produces another E plus E. So you have E plus E. Each one of these E could produce A. So it's basically the same. I mean, the grammar, this grammar and the earlier one, both actually give us the same language. And this certainly is simpler, more intuitive. It very clearly tells us what it does, what it means. So why don't use this language? Okay. Let's try to do that. So I do again. I mean, the main does not change; it's the same. So I call E. Now I come and I call E here. Again, what do I have to check for doing between this as to whether we have? I mean, what is the first of E? First of E is A. So I check if it is A. If it is A, I match. I control. Now is the big question. The question is, how do I know whether I have this A is actually the terminating A which produces, which is produced by the second production loop, or I must recur with the first production loop? See, the difficulty is that here is a non-terminal which replaces itself on the right-hand side as the leftmost symbol. So when I go here, I have E actually calling E again. And we all know that a recursion needs a proper exit condition. But here, I have not consumed any symbol because I cannot, because E is directly calling E. E is directly being replaced by E. So it's a plain and simple recursion. I do not know how many times should I recur before I start actually coming back. So this eventually turns out to be an infinite recursion. For example, if you this is just a direct coding of this. So let's say I do A plus A. I come here, E. A matches, match A. I'm here, E. Okay. I'm calling E. Now, mind you, I come here. I call E. I've called E. What is my L? I've matched this A. My L is plus. And this match fails. This match has failed. Because, why did it fail? Because by matching this, I have actually guessed production rule 2. Whereas I needed to do production rule 1. So I should not have matched A right away and B here. I should have matched it inside so that the next match would be on A plus. But I have no way of knowing it because I do not know how many times this will occur before I get to use the second production. So this is a symptom which is the killer for the recursive descent parser. That is, you cannot have a recursive descent parser if your grammar has a left recursion. That is, if there is any production rule where the right-hand side, the first non-terminal or the first symbol on the right-hand side is same as the non-terminal on the left-hand side. Now, when I say this, you should also be very careful to remember that a recursion is not always direct. So if I have a production from a non-terminal A which produces B, non-terminal B followed by something, and then I have a production from non-terminal B which has a production with non-terminal A followed by something, that too will not be amenable to recursive descent parser because you will again have a mutual recursion which brings back the control to the non-terminal without actually giving you a decision point to consume an input. So left recursion is what is kind of the killer of the recursive descent parser, and kind of a problem with the top down. So this kind of simple grammar cannot work easily for a recursive descent parser. We need to do something about them. Okay? Okay, so let me again stop and see if there are questions.
Sir.
Yes.
Sir, in this means.
Could you please identify yourself?
Yes, sir. I am Soumitra Das.
Yes, Soumitra, tell me.
Sir, this code, if I take the expression plus a dollar sign, it will take it, right?
If you take the expression as?
Plus a dollar sign.
Let us go back and see what it will do. You are talking in here?
Yes, sir. Means if I check with plus a dollar sign.
Plus a dollar sign. So
yes.
So we are here, right?
Yes.
So this will not match.
Yes.
Right? Because we have plus. Your L is plus, right?
Yes.
So you will call E.
Yes.
Right? You have come here.
Yes.
Right? You have not done any match. So L remains to be plus symbol.
Yes.
Right? So this does not match. You call E. You'll come here. So you'll simply have an infinite recursion.
Okay. And sir, what in the case of a plus a dollar sign? Please
A plus a dollar sign is you are here. So L is A, right?
Yes.
The first A.
Yes.
You match.
Yes.
So your L becomes plus.
Yes.
Now you call E.
Yes.
Now you are in the same problem.
Yeah.
Right. So that's the difficulty. That's the difficulty because you are not getting the clue in terms of whether to see if it is a recursion, there will have to be an exit. Right? So the exit is using the second production, but you cannot guess that by looking at the first production. So you do not know when to use the second production and when to use the first production.
Sir, I can, sir, can we use the dollar sign After
Oh,
matching A, if he see that the
where do you know where is the dollar sign? Dollar sign could be after 20,000 characters.
after this when the string ends, there will be immediately there will be the dollar sign.
Yeah, but you are not consuming here anything. Just Shomit, just observe A plus A dollar, right? So you have to match an A to see whether it is a second production. Right? So you have
Yes.
done that, and after you have done that, you are left with plus. So you'll keep on just recurring. See, the question is not whether you can find a way of writing this. The question is, what I'm trying to illustrate is this very straightforward way of coding production rules in terms of a set of co-recursive functions, which immediately give you a recursive descent parser on almost no effort, no brainer. Antler does that. Antler generator does that. I mean, very quickly you get a parser. May not work even for very simple grammar if there is a left recursion.
Okay.
Now, how you can handle is a different question. That is what we will have to answer. You know, naturally, we will have to take to other techniques to be able to do that. But that's the problem that I'm highlighting here. That the left recursion and the left recursion, as we'll see, is something which is very, very important in terms of the common grammars of languages, because as you can see, the left recursion is representative of the left associativity of operators. You have left recursion because you have left associativity of operators always happen on the, not always, but majority of your operators have. So all of those operator productions give rise to left recursion. And there are several others, as we'll see.
Okay, sir.
Any other question? No, doesn't seem to be. Okay, let me go back and continue. Yes, yes, please.
Sir, can we convert left recursion to right recursion and then apply this type of algorithms?
That I mean that's the next step we are going to do. So we'll discuss. Any other question? No. So let me go back and kind of continue with what Aryaman was suggesting. So let us look at two issues of recursive descent parsers, top-down parsers. So the first issue is what we have already discussed, which is the left recursion. So we said this is now I'm putting a formal definition of this, so which you should learn. A grammar is left recursive if and only if there exists a non-terminal A, at least one non-terminal A, that can derive to a sentential form with itself as a leftmost symbol. Right. Just see that the definition is written with a little bit of trick. It does not say that it has a non-terminal A which has a right-hand side, which starts with A, because that could be co-recursion. So it is saying that if there exists a non-terminal A that can derive a sentential form, so you have a non-terminal A that is doing a derivation, and this is a typical way to denote, double arrow right-hand side is the derivation step, double arrow right-hand side plus, I mean, you are kind of borrowing from the regular expression notation. So it says one or more steps in the derivation. Through one or more steps in the derivation, if it can produce something like A alpha, alpha, you remember, denotes a string over terminal non-terminals, including epsilon. So if this can happen, then we say that the grammar is left recursive. And it is all that you need is a single non-terminal having this behavior. There could be multiple non-terminals having this behavior. And if that happens, then we cannot have a recursive descent or predictive parser with this left recursion, because we do not know how long should we recur without consuming an input. So that's the basic point. keep on. Everything comes on the right. So if we illustrate, how does it look like? How does this left recursion look like? So I'm taking a very simplified example, but the most fundamental one. I'm showing that the most generic form of the left recursion is A produces A alpha. Alpha could be any terminal, non-terminal. Naturally, there will have to be another production from A so that this process can end, and wherein A produces beta, where beta does not start with the non-terminal A. So this is given this production, what is the language that it produces? Now, if we just do the derivations, then A produces A alpha. That produces, you use it one more time, A alpha alpha, A alpha alpha alpha. So it will keep on producing a chain of alphas till you use the second production at the end, which starts with beta. So you could just use the second production, or you could use the first production one or arbitrary number of times before you use the second production. So what you eventually generate is beta alpha star. And if you look at the tree here, I have used a drawing tool for doing this parse tree, which does not allow me to write an alpha or a beta Greek letters. So what I write as small a here means alpha. What I write as small b here means beta. So this is what it is doing. Starting from A, you have A alpha. Then the second A is A alpha. The third A is A alpha. Keeps on happening. And then what you have got in this way is A alpha star. And finally you produce it. So if you read this from left to right, it is beta followed by alpha star. That's the first. Now you can remove the left recursion. You can make this. That's what Ariman was saying. Is you can make this into a right recursion. That's all that you do is to rotate this tree. Just rotate this tree. I mean, think about a right rotate this tree. So this comes on top. Instead of this A being the starting non-terminal at the root, this A becomes the starting non-terminal at the root. That's what I've done. And change these symbols as A primed. So what we do is we first produce this beta, because this has to happen. Because we can see that in the actual sentence, there's beta followed by a sequence of alphas. So we generate the beta and produce another non-terminal A primed, which can recur to produce the alphas. And this can produce it in a right recursive way. I do not need to produce it as A producing A alpha. I produce it as A prime produces alpha A prime. So it's always so the advantage that you get when you are trying to code this in terms of the recursive descent parser function, you will write a function for A which will have beta to consume. So you will have at least one symbol in the look ahead to consume to decide that you are using this production. And after having consumed the whole of beta, then you will call A prime. And in A prime, every time before you go into the recursion, you will have some alpha to consume, at least one symbol to consume. So every time you recur, your input becomes shorter. And therefore, since your input is finite, your recurrence will also have to be finite. And that solves the problem. Necessarily gives you the same dimension. Your parse tree is being rotated. So you can solve this issue of left recursion, which is a showstopper for recursive descent parser by converting it to the right recursion. That's a simple way of doing it. Okay. So let me show you that for a very standard grammar that we have already introduced. This is a grammar involving addition, multiplication, parenthesis, and identifier. So it is all arithmetic expressions where parenthesis with identifier and all this, where parenthesis obviously has the highest precedence, then you have the star and finally the plus. Now you can see that the plus and star here are written in this grammar as left associative. Just look at ID plus IDs plus ID. This is the parse tree. So E produces E plus T. E1 produces E2 plus T3. I mean, just numbers are given just for being able to identify different E's and different T's. Then this E2 produces E3 plus T2. E3 produces T1, that's production rule 2. T1 produces F1, production rule 4. F1 produces ID1, production rule 6. Similarly here. So what happens when I want to evaluate what will happen? Certainly, I have values in these identifiers. So I'll keep on propagating these values up. And I will be able to get value for this non-terminal E2 and the non-terminal T2 and be able to do this addition to do the value of E2. Until I have been able to do that, I would not be able to do this plus because the value of ID3 will propagate and become the value of T3, but this value is not. So this obviously tell me, and we have seen this earlier in terms of the syntax tree also. I mean, as you can figure out, the only difference between the syntax tree and the parse tree is parse tree does show you all these non-terminals on the tree as well, whereas the syntax tree was just showing you the terminal symbols, but the effect remains the same. This plus is lower down in the tree, so it has a higher precedence because unless you have done this, it has a higher. I mean, let's not talk of precedence. It is lower down in the tree, so it has to happen earlier in the computation. So unless you do this plus, you cannot do the other plus. So which tells me that between ID1 plus ID2 plus ID3, the first addition has to happen necessarily earlier than the second one, which makes plus to be a left associative operator. That's what this grammar is saying. Similar thing will happen with T star F. So now you can make out what does dictate that this is left associative. This is left associative. Which property of the grammar tells you that? That is told by the fact that E produces E plus T. That is, there is a left recursion. If I had written this as E produces T plus E, then there'll be a right recursion. The tree will be right rotated, and your plus operator would be right associative. Right? So that's the basic. Okay. Now let's see. I convert this in terms of removing the left recursion. So I do the same thing here. So I have two productions here. Here's the left recursion. This is my. If I just refer back to A produces A alpha, A produces beta, and this is how A produces beta A primed, A prime produces alpha A primed. Is a change that we are making. So we have to understand what is beta. So beta A, E is A here, alpha is plus T, and beta is T. So I do A produces beta A prime, E produces T E prime, and then A prime produces alpha, that is plus T E prime. So this now becomes a right recursion or epsilon to make this process terminate. Okay, that's what it is. Now the same thing is done between these T produces T star F and T produces F. The left recursion is removed. Rest of it is. Now, if I produce the same ID1 plus ID2 plus ID3 using this grammar, this is how it looks. This is ID, this is T produces, because this ID has to come from T produces FT primed, T prime becomes epsilon, F becomes ID. You get the ID here. Similarly, ID2 here, ID3 here. You can see that, I mean, you have epsilon productions and more things coming in. So the tree kind of looks a little bit more complicated, but I mean, once you understand that this whole subtree is actually producing an ID, this whole subtree produces an ID, this whole subtree produces an ID. Mentally call them as IDs. So then you have ID plus ID plus ID. But what is the position? This plus, the second plus in the expression, this plus in the expression is lower down in the tree. So certainly if I produce in this way, I will not be able to do this plus till I have done this plus, because this has to happen earlier, because this is what it will get This is what will get the value before this gets the value. So syntactically, I have been able to handle this. Syntactically, I have been able to make it amenable to recursive descent parsing, top-down parsing. But is this removal effective? It is not in a way, because I have, in this process, I have actually destroyed the associativity of the operator. Operator has now become right associative. And that may not be, in semantic terms, that is not something that I may want to do, or that may be possible, allowed, in terms of using the translation that I do from this grammar, because I finally am interested in the translation. So that is the syntax semantic issue of left recursion. So we can see that syntactically it can be removed and put into right recursion. True, that solves part of the problem and makes it easier to write grammars, write parsers in recursive descent, but semantically it will continue to cause further difficulties because of this corrective transformation that we have. So that is one issue that I had to discuss. Let me look at other issue. The other issue is, I mean, I'm referring back to kind of here. I'm fascinated by this grammar because it's so simple to say. It's so intuitive to say that expression is expression plus. That's it. Other than an identity. So can I say that in general? The same grammar which gives me all the expressions involving identifiers, parentheses, multiplication, and addition, can simply be put in terms of this grammar, which simply says expression is expression plus expression, or it's a multiplication of expression, or it is parenthesizing of expression, or it is simply one single identity. Now this so this makes it ambiguous, because if it is, then I do not know if I have expression 1 plus expression 2 plus expression 3. I do not know. According to this grammar, according to the first tree, I would not know which plus to do first. So the ambiguity makes it simple, but it kind of leads to losing the associativity information, also losing the precedence information, because now I can write ID plus ID star ID. I do not know which one to do, the plus or the star. Okay, so the trade-off is between having a simple intuitive grammar and losing this information. But then there's a good solution that we have already seen in terms of the early example we did for infix to postfix. We said, okay, fine. If the grammar is ambiguous, we can still live with that, because I can specify the associativity and the precedence in terms of an operator precedence information, operator precedence table, which gives me a very nice clue in terms of how to resolve the ambiguity. Right? So when we have such issues like I have that kind of an ambiguous grammar, you can see the kind of different parse trees that can get generated. This is a possible parse tree. This is one derivation. The same sentence. I'm just showing you the same sentence has two different derivations. Right? So this is one derivation and this is another derivation. And according to this derivation, I've formed this parse tree. E produces E plus E. E produces E plus E. Then this E produces E star E. This E produces E star E. This E, third E, which is E5 here, produces ID. Second E, which is E4 here, produces ID2. The first E produces ID. Right? So rightmost derivation, and there is a corresponding parse tree. I could have done the same. I could derive the same string using this ambiguity in another way. This is the other way of deriving it. So E produces E star E. Then this second E, which is E5 here, produces ID3. Then the first E, which is E2, produces E3 plus E4. Then E4 produces ID2, E3 produces ID1. What is the difference? Look at the first trees. Here, in the first one, the star has to happen first before E3 gets something, and then the plus will happen. Star has a higher precedence. Here, plus has a higher precedence. So this is the wrong precedence. So that is the choice that we want to make. That is the choice that we want to make. That if the grammar is ambiguous, then I can choose. I have multiple syntax trees, multiple parse trees, and I have to choose the correct one. And to make this correct choice, I'll use the precedence and associativity of operators. Just to show you another example, this is another example of expression ID star ID plus ID. You have one parse tree here, you have another parse tree here. Certainly this one is correct because star is lower. This one is wrong because plus is lower. So this is so what we would have liked to use is something like this, which is ambiguous, left recursive, everything. But to make the recursive descent parser work, we have to first remove the ambiguity. And this is what, removing ambiguity in this way is not easy as an automated process. Often an automated process is not possible. You have to do it kind of manually, understanding. So I'm using this. I have used multiple non-terminals to layer the grammar. So the higher up on the grammar in terms of the non-terminal means that you are associating with an operator which has a lower precedence, because higher up is in the tree. So if you are higher up on the tree, then you have a lower precedence. So the non-terminals are layered in that manner, and every non-terminal is taking care of one operator. And so that this ETF differences take care of the precedence, and then this left is recursion here take care of the associativity. So this grammar to this grammar, the simplicity gets lost, but the interpretiveness gets very, very clear. This clearly says that plus is left associative, star is left associative. Star has a higher precedence than plus. It says parenthesis has to be done first because it is at the lowest level of the operation. And then because it has, so this just has ambiguity gone, since it still has left recursion is what you convert and make this into. And you know what difficulty it gets into. It gives you the right, it gets you into right recursion. Things get a lot more complex. You can see that there are more production rules coming in. Your parse tree becomes bigger and bigger. Hundreds of epsilon productions, which are kind of useless. Your semantics has become completely destroyed because something that you wanted to be left recursive is now right recursive and so on. But this is what your standard process would be if you want to do a recursive descent. So as we'll see that, because of these difficulties, it is customarily more often that we will use the top-down or the recursive descent kind of parsers. There are non-recursive versions of top-down parsers. These are called predictive parsers, table-driven ones. I will not go into those discussions because we do not have the time to discuss all different variants, but there are table-driven ones as well. But what we will try to do is to finally come to a form of a parser which can work with some very easy way. It can work with an ambiguous left or right recursive, every kind of grammar. And we'll go on to the parsers for those. So at this point, let me stop before we move on further in case there are subsequent questions.
One question.
Yes. If there is any question, please ask or put on the chat box.
It's on the chat box. There is one.
Sir, as the grammar is left recursive, can we derive a regular expression for it? No, dear, you cannot. I mean, you can write a regular expression for the grammar form, but the grammar is left recursive does not mean that it is a regular grammar. It's a context-free grammar. So if it is a context-free grammar, its language cannot have a regular expression, right? You remember the pumping lemma and all that. So left recursion is something which is the property, a structural property of a grammar. So you also have, when you talk about regular grammar, you say that you have left recursive way of writing the grammar. A produces AA or B. Is a very typical way to write regular grammar. But the basic point is the grammar itself here is context free. So the language it generates is a superset of regular language. And therefore you cannot in general have regular expression for that. Okay? So any other question?
Nothing, it seems.
Okay, good. So let me then continue and okay. So I'll continue and I'll start going into the other class of parsers, which are called the LR or the bottom-up parsers. Now, before I get into that, I just want to remind you that since you have done flat, you know that context-free grammars will have recognizers which are PDAs, right? Push down automata. Right? So when we did the lexical analyzer, we were able to express our specification in terms of regular expressions or regular grammar. And therefore, the lexical analyzer that we eventually built was a collection of finite automata, deterministic finite automata, because that's what the regular expressions will lead. When we are talking about parsing of context-free grammar in general, the syntax analysis here, certainly every time it has to be a PDA of some form. And let us note that unlike the situation of the finite automaton, where the non-deterministic finite automaton and the deterministic finite automaton are of equal power, in the sense that if I have a non-deterministic finite automaton, then I can convert it always to a deterministic finite automaton. Okay? So that gives us a very nice process of synthesizing lexical analyzers by converting regular expressions into NFAs and NFAs into DFAs. But when we'll talk about parsing of context-free grammar, we have to keep in mind that NPDAs are more powerful than DPDAs. That is, non-deterministic push-down automaton is more powerful than deterministic push-down automaton, which in other words mean that there are several non-deterministic push-down automaton for which there is no corresponding deterministic push-down automaton. Now, quite obviously, since we are not looking for a theoretical characterization of a recognizer. We are looking for a program coded implementation of the compiler of the parser. We have to only synthesize deterministic pushdown, right? So our construction process has to always have an eye on that. So please keep that point in mind. One. Second is in terms of whatever way, whether we do top down or we do bottom up, at the end of the day, if it is recognizing a context-free grammar or the language of a context-free grammar, then whatever we generate, whatever we have made, must be a DPDA, must be a deterministic pushdown. So if you think about the recursive descent parser, the recursive descent parser actually is a DPDA. Why? Because you have a set of functions and the functions are recursive. So every time a function is recursive, you know that it actually has a stack model. The stack on which its recursive calls are upped one after the other, right? And it consumes and so on. So it's actually is a DPDA. Now the question is whether I synthesize that DPDA as a set of recursive functions, where often maybe your actual tasks are achieved in terms of tail recursion or at times in a more complex way, or whether I can do the same thing in terms of a more formal structure of a DPDA where I have an explicit stack managed by us and a table, DPDA table, which drives the way you push a symbol to the stack or pop a symbol out of the stack or make the change of state in the driver finite automaton, is a choice that we make for different classes of parsers. So whether it is top down or it bottom up, it necessarily is a DPDA. And even in top down, we have seen the recursive descent one, which is with an implicit stack. We have a whole class of parsers called predictive parsers, LL1 being the most popular of them, which are more explicitly in the structure of DPDA. But for our current study, we are just staying away from that. But if you use a generator like Antler, which is a very popular generator for top-down parser, it actually generates an LL1 parser. Right. I mean, if time permits towards the end, I'll talk a little bit more about LL1 parser. But let me now move on to the other class of parsers, which are called the bottom-up parsers. As a class, most of them are called LR parsers. We'll understand what LR means. But they are also called shift-reduce parsers. Right. So let me slowly give you and get you started with an example of such a parser. So what I'll do is I will actually present a parser to you, which is a shift-reduce parser. I'll show you how the parser actually parses a string, and then get into the fundamentals of how to construct such a parser. So we'll just do a little the reverse way. First, take an example and see how does the parser work. So I use this, this kind of is a continuing grammar for us. So this is a sample grammar of expression, which by now you are got familiar with, for which I'll present you a shift-reduce parser. Now, it is a DPDA. Has to be, right? That's me. So I need a parsing table. I need a kind of a PDA table. Or a PDA, decision maker, wherein I can take two types of decisions. One is the decision of changing states of the controlling DFA. Right? Every PDA has a controlling DFA. So I need a state changer. So I need a state transition information. And the second is I need information. I need clue in terms of what we push in the stacker and what we don't. Right? So when do we push and when we pop? Right? So that is what in this parsers, this whole class of shift-reduce parsers are done by this kind of a table. So let me explain you what these codings in the table mean. First of all, note that all production rules here are written with a number. The numbering is arbitrary, but every production rule has a specific number. So if you remember that, so there are 6 production rules. In this whole table, if I decode the table, let's see what the structures are. Different rules of this table are states of the controlling finite automaton. So this finite automaton has 12 states. So that is what will decide what the PDA is doing. Okay. Now, what are the decision points? One part of the decision point is the action set of columns, which is being in a state, the DFA looks at the current input symbol in the input buffer. So if I again go back to the grammar, then the input symbols could be plus, star, opening parenthesis, closing parenthesis, and ID. So plus, star, opening parenthesis, closing parenthesis, ID, and we will specially accommodate dollar to mean the end of it. So every entry on this action, basically it tells us as to given this state and this input, what action should the DFA take? So that's the whole point. So you can see that this is kind of a coding of a state transition. Now, what are the actions that the DFA can take? DFA can take any of the 4 actions. One action that it takes is known as shift. The word shift. Shift is the input symbol that is currently being pointed to by the DFA will be removed from the input and will be pushed to the stack. It is a PDA, mind you, it is a PDA. We are working on a PDA. So there is a stack. There is a stack of symbols. So shift is an operation by which you remove the input symbol from the input buffer and push it into the stack. All shift operations are shown as S. These are all S's. Along with the S, you have a number. This number is the number of the state. So it says 2 things. This entry actually says 2 things. One, it says shift. That is, if in state 0, if the input symbol is ID, then you shift it from input, push it to the stack. And you change the state of the DFA to 5, state 5. So that this encodes the state transition. So it gives you one action of shifting symbol from input to the stack and also gives you a state transition. So if I have in state 1 on plus, I have S6, it tells me that if the DFA is in state 1 and if the input symbol is plus, then remove that input from the buffer, push it to the stack, that is shift, and the current state of the DFA becomes state 6. So this is the first kind of action called the shift action. The second is called the reduce action. Reduce R. So mind you, we are talking about bottom-up parsing. So we are talking about starting from the final sentence and coming back in the reverse order to the start symbol. And in every sentential form, we need to identify the right-hand side of a production that we reduce by the corresponding left-hand side, non-terminal, to get to the previous sentential form. Just to remind you on this, allow me to take you to the derivation and we had discussed this. So we said this is the rightmost derivation. So this is the sentential form. I identify that this underscored ID is the right-hand side of a production. I replace that by its left-hand side, which is F. I identify F as the right-hand side, replace it by T, and so on. So this process is known as the reduction. So in the reduction, you are taking the right-hand side of a production and replacing it by the left-hand side. Let's see how does it span out in the shift reduce parser. So now in here, you are saying that, let's say here in state 2, if the input symbol is plus, then you are doing R2. What does that mean? It means that you will reduce by production rule 2. R2 is rule 2, reduce by 2. Which means that on the top of the stack, you should be able to see the right-hand side of this production rule. So if it is R2, then the top of the stack would be the symbol T. And I should be able to reduce by that, which means that I take out that T and put in the left-hand side symbol E. I do not do anything with the input. I do not change anything in the input buffer. Unlike shift, where I remove the input and put it to stack here, I just look at the input and do nothing on the input. But the input is the clue in this state to do this reduction so that I can go one step backward. So this input is known as the look ahead on the reduction. So as I do this reductions, let's take another case. Let's take a case of, say, R1 here. So if I'm in state 9, and if my input symbol is closing parenthesis, my action is R1, which is reduction by 1, which means that on the top of the stack, I expect to see E plus T, all these three symbols one after the other, so that I will be able to take out three of them one after the other, E plus T. Thrice I take out, I get E plus T out. And then I put back E, which is the left-hand side. And when do I do that? I do it in the state 9 if my input symbol is closing parenthesis. I do it in state 9 if my input symbol is plus. I do it in state 9 if my input symbol is dollar. And in none of these cases, I change anything in the input because I'm just doing a reduction. So, okay, so that does the reduction. The next question remains is, well, I've taken an action. So what is the next state? What is the next state? In case of shift, the shift itself told me what is the next state. In this case, it does not. Right? So getting the next state is a little bit more tricky, and that is where we use the goto function. As we take out the right-hand side of the production rule, we will expose some earlier state, and we'll have to, based on that earlier state and the input that you have put in, we'll have to decide on the next state. It will become clear when I show you the working of an example. So we have shift state, we have shift action, we have reduce action. These are the two types of actions in the table. The third is accept. Accept is an action which happens when you reach a state and an input where you say that the PDA has accepted. So you know there are different ways of accepting PDA. It could be by, empty stack. It could be in terms of, reaching a particular state in the DFA. It could be in terms of saying that the input is exhausted and so on. So, things will get mixed in all that. But what is typical for shift reduce parser is naturally the input has to get exhausted. So accept will only happen on dollar and in a certain state. So it is accept by state in the PDA here. So wherein you know that you have been able to successfully parse the input string and reach the accept state. So you're happy. So there's a accept action terminates everything with a positive. So three actions: shift, reduce, accept. The fourth action is failure or rejection, reject. Now, in this whole table, you'll say that there is no reject written. Anything that any cell that is not filled up is a reject, which tells you that given a correct input stream, this parser, this PDA is not expected to ever reach this configuration. For example, if you are in state 1 and your input is star, then you do not have an entry, which means you are in a reject state. That means you have reached a configuration in the PDA wherein you cannot proceed any further. You have a wrong input. So you can see there's a whole lot of reject situation, and therefore to keep the table look simple, we keep the reject states as not written. We have shift, we have reduce, we have accept, and we have reject. These are the four actions that this shift reduce parsing table will have. That is the meaning of this parsing table. Okay, I'm sure that things are still very confusing. So let me start with an example. Okay. So this slide is what you should spend a lot of time by yourself doing and creating. So just for reference, I have reproduced the shift reduce parsing table here. It is same as what I have here. I've just made it so that I don't have to keep changing slide. Here is the string that I want, that I have in the input, ID star ID plus ID, ID star ID plus ID. And in this, I show steps are a trace of how does your PDA work with this input, given this shift reduce parsing table. So it starts with state 0 being the first state. So you have a stack I think somebody has got unmuted. Could you please have mute? Okay, thank you. So this is a stack of states, and this is a stack of symbols. Let's see how does that work. And this is the input. So I will continue, keep on taking the input. We start with this state, and the first step is a state on the top of the stack. At any point of time, the stack has a state on the top, obviously, because it's a stack. And that is the current state. That's the meaning. Right. And on the right column is the action. And we know there are 4 possible actions: shift, reduce, accept, and reject. Since this example is for a correct input, we will not have the reject action. Okay. So we start here in state 0, and this is my input. So the input that I'm looking at is ID. There's the first input, state 0 ID S5. So which means that my action in this is shift, and as I shift, what will happen? My state will change to 5. So my state changes to 5. I put that push that state in the stack. I remove the input ID and put it to the symbol stack ID. So I could have mixed these two in the same stack, the stack of states as well as stack of symbols, but I find it easier to understand if they are shown separately. So I will see that it really doesn't matter as long as you keep the count right. So I'm using a stack of states, I'm using a stack of symbols. So I put it. So that is shift. I said that you remove the input symbol from the input and put it to the stack. Right. And the next state is 5. So now what is the next configuration? Your current state is 5 and your input is star. 5 star. 5 star is R6. 5 star is R6, which is, what is R6? Actually, I should have written the production rules here. R6 is reduction by production rule 6. So what does that mean? That means that I'm here. Look at the sentence. I'm here. ID is what I have found. and should be replaced. ID is what I found which should be replaced. So I can reduce by F producing ID, which means I'll remove the ID from the top of the stack. That's the right hand side, and replace it by F. I remove ID, I replace it by F. That is reduction by F producing ID. Now what happens? As I remove ID, this is, please listen carefully. As I remove ID, I'm doing a reduction, I'm going back. So on my state machine, I go back as many steps as I go back in the symbol. So this ID came in with 5. So as the ID goes out, so that the state 5. So I take out ID, I take out 5. And my exposed state becomes state 0. My exposed state becomes state 0. I take out ID, I put in F, the left hand side. So I have a configuration where my exposed state is 0 and my symbol is F that is coming in. I check it here, 0, F, the state is 3. My next state is 3. So this is what I said, that it is a little tricky to get the state transition when you have done a reduction. So what you do, you remove the right hand side of the production because you are reducing. And obviously the corresponding states you have to remove, which is easy to do because there are as many state transitions as there would be symbols on the right hand side. Why? Because in every symbol comes into the stack by a shift, and every shift changes one state. So if the right hand side has 3 symbols, there'll be a sequence of 3 states corresponding to those symbols having been come inside the stack. So you remove the right hand side and you remove as many states from the stack as well. So I'm removing ID, I remove 5 from that. 0 gets exposed. I replace, I'm doing reduction by 6 because that was my 5 that was my 5-star. That was my 5-star action, reduction by 6. So I remove ID, I push in F. So my exposed state is 0. My symbol is F. So in 0, I look at F, which is 3. I put in 3. This continues. Now what happens? So I've come to this sentential form. Now look at one thing very carefully. You'll see that very nicely coming in. As you go, you are doing a bottom up, you are going backwards. Try to read the sentential form as the continuation of the stack of symbols and the input. So this is your sentence. This is F star ID plus ID. Just read them together. Is this sentential form? Then will be T star ID plus ID. Then you have this. You have T. So you'll keep on getting T star ID plus ID. It'll just keep on getting them in the way the sentential forms come. So let's take a look. So now we are in state 3. This is symbol F and input is star. 3, input is star. Okay, again, reduction again. This reduction is by T star F. You can see here. This reduction is by, T producing F. That is R4. So I take out F for reduction, right hand side. I take out one symbol 3, one state 3, because I'm taking out one symbol. 0 is my current exposed state, and T is my new symbol going in the left hand side. So 0T is 2. So my next state becomes 2. Then I have 2. So I have come to T star ID plus ID. I've come to this sentential form. Then I have 2, I have star. 2, I have star, which is S7. So star comes in from input, is a shift. Star comes in to the input, state changes to 7. I have 7 ID. 7 ID is shift 5. So ID comes in, state changes to 5. So now I have T star ID plus ID as it continues. 2 symbols have got input to the symbol stack, and now we have 3 corresponding states corresponding to that. Now we have state 5 input is plus. State 5 input is plus. it is reduction by 6, which is F producing ID. So this is the reduction that is going to happen. ID here, F producing ID, so the right hand side will be removed. ID is removed, replaced by F. ID 1 symbol is removed, so the corresponding state 5 is removed. Export state becomes 7. New symbol is F. 7F. My state is 10. So I put the state 10, and I have the new sentential form T star F plus ID. Then again in 10, I have plus. 10 plus is R3. What is R3? R3 is T produces T star F. I have T star F on the right hand side. I'm here. T star F for the right hand side. So I have to remove that right hand side and put in the left hand side. So I remove all these 3 symbols, put in T, and as I'm removing 3 symbols, I remove the corresponding 3 states. I'm going back. I remove 10, I remove 7, I remove 2. My exposed state becomes 0, and I've put in T. So in 0, T, my new state is 2. So 2 goes in. That is my new state. And I'm in T plus ID. This. And it goes on. On 2, I have plus, which is R4. So this is, 2 plus, that is R2, which is E produces T. So I reduce by that, T is replaced by E. 0 gets exposed, 0 E is 1. So I have 0, 1 E, I get E plus ID. Then 1 plus is S6. So plus is shifted. I go to state 6. 6 ID is S5. So ID is shifted. I go to state 5. Then $5. Now I have $5. $5 is R6, which is reduction by F producing ID. So I do that reduction. ID gets removed, gets F. 5 gets removed, 1 state. 6 is the new exposed state. F is the symbol. So 6F is 3. So this becomes 3. Now you have $3, which is R4, which is T producer reduction by T producing F. So I'm here E plus F dollar. Now I'm going to the next one. F is removed. 1 symbol is removed, replaced by T. 1 state is removed. I get 6. Now I have 6T. 6T is 9. So 9 comes in. In state 9, I have dollar, which is R1. I'm in this sentential form. So I reduce by E producing E plus T. So I remove 3 symbols E plus T. I remove 3 states 1, 6, 9. I put in E. Exposed state is 0, and E is my next symbol. So 0 E is 1. So I put in 1. I get $1, which is accept. So I accept this. So this is, I know it looks like kind of a magic, and you can try several strings with this parser table through this process to get. I did not do more examples to get convinced that this actually works. And if you try with any wrong input, and you'll see that. For example, a very simple thing you can postulate here. If I just had ID followed by ID, so I will come in here, and instead of a star, I will have an ID coming in here. ID followed by ID. There's some wrong input. So what will happen in 5? I will have an ID. In 5, I have an ID. That's a reject. I clearly know that that's a reject that will happen. Okay, so that's kind of the basic way a shift reduce parser works. I mean, this does not obviously tell you how this parser is built. I mean, the whole of it is basically this table. I mean, given the grammar, how you get to this table is the whole of the parser construction. That is what Bison will do for us. But given this parser table, this is how the parsing will happen, and this is how the actions will happen. And these actions are what are going to be the most important thing for us. because that is what will tell us how to construct the parts tree, and more importantly, that is what will tell us how to translate, what to translate at what point. I think with that, I will stop today and check if there are some questions pending on what I have discussed.
There are no pending questions on the chat.
Is there any questions on this? And again I'll ask if some of you could volunteer and say that if the pace is right, or if it is slow or fast, or if there are difficulty areas coming up, because this is a very core of the compiler construction theory. And given the short time that I have, I'm trying to do things more through examples than getting into very hardcore theory, because finally we need to know how to use the generator tools well to be able to do things right. But if I'm going fast or if I'm going too slow, just let me know. Maybe somebody can comment. I mean, you don't have to have a question. You can just have comments on how things are going, or what you would love to see more. No volunteer to comment.
Jyoti has a comment.
Pace is just fine. Okay, that's the simplest thing to say, but then okay, fine if it is fine for all. But
just one thing.
Yeah.
One thing. Just can it help if we have this state transition diagram side by side with the table?
Yes, it can. It actually can. I mean, if we draw it out,
because directly from the grammar table, it seems a little complicated.
Yes, that is one, and second is particularly when we are reducing, and we are removing states from the stack. It is not clear that we are actually tracing back on the path in the DFA. That is actually tracing back the path that you had taken to reach this state. So that is not clear. So I'll try to do that. Actually, this is, but it has to come in the same slide. That was my problem, because
the mine has a similar related question. How are the states decided?
Let me. I did my presentation. Picking around. Yeah, so maybe here I will try to generate that diagram and put it. Yes, because actually you need to see everything together to be able to understand this really well. I'll do that. Okay. So what is the question? Let me go back. How are the states? I mean, that's by the parser generator. I mean, that's what we are going to study in little bit more details in the coming lectures as to how you decide that table. So that deciding that table is not only the structure is clear. The columns are decided because the columns are the input symbols and the non-terminals. But the rows are the different states, how many states you need, what way you can write the grammar so that you have less states, more states, what you do in actions you have in every state. Those are the part of the design of the parser algorithm. So we'll do an outline of that. We will not do an in-depth of that. And then I'll show how you can use Bison to get that table generated. Right, so that will be our so I think if we could get some intuition on why this type of transition working, it would be better. Yes, of course. We will do more of this. This was just to first show you the working of the model, so that you can map it to the basic theoretical understanding of having a PDA, DPDA actually working for you in the state. So. As Professor ISG has suggested, I will show the state transitions also in terms of a diagram, and we will explain some bit more as to why this is working, how this is working. And for this, we need to introduce some more notions, like the notions of first, follow, and what is a handle. And we will do that when we discuss LR parsing in greater depth next week. Okay. I think we are out of time and there is no other question right now. So have a nice day. We meet again on Thursday in the laboratory. Just to remind you all, on Thursday we will have two things happening. One is Professor ISG is going to tell us about runtime environment in greater depth. So there'll be an exciting discussions on that, getting into minute details of how the runtime is managed. And then at 4 o'clock for half an hour, we'll have a trial quiz, which is getting prepared for the next quiz in the next week, wherein a separate Moodle server is being set up for conducting the quiz. You will get the details in the mail, but the details will be available about an hour before the quiz actually starts. It will be a half an hour quiz having some 7 or 8 questions that the TAs are setting up. And this will be a non-evaluate quiz. So you will get to see your evaluation, but this will not add to the credit. It's just for all of us to get accustomed to the whole process of doing this online quiz. Okay. So these are the two things to happen. This will happen at 4 o'clock. And from 2 o'clock, as usual, Professor ISG will take your class. Thank you then. Have a nice day and take care. Stay safe. Bye.